Just some more outside college physics here. What are we going to look at? We're going to look at a nice little problem involving a projectile that, well, investigates a little bit more of what do I have to do in order to make something specific occur. So here's the what if portion here. What if I wanted to take this ball right here and I want it to be, say, a certain distance away from this whiteboard here. We can measure that out, say a meter away from it, maybe 2 meters away from it. And I want to take this ball and I want to throw it at a particular angle, say like 50 degrees, and I want to strike that little X right there. Let's not put that too high up. So that X, I'm going to throw it from this level at 50 degrees. And that X is a certain displacement Y above the level that I'm throwing at, and it's a certain displacement X away from me, right? So if I'm throwing it at 50 degrees, what velocity do I have to initially give it in order for it to hit that spot? Well, if I throw it too hard, it hits up too high. If I throw it too soft, it hits too low. If I throw it just right, or at least close. Anyways, there's a particular velocity that I need to throw it at that particular angle of 50 degrees that actually gets it to strike right there. And harder than it seems, right? Well, I'm not a machine. Anyways, I'll stop now. Let's just calculate it, right? And then we can design some apparatus that actually shoots it out at the right speed. Some little variations. So here's the problem. All right, so we got ourselves a soccer ball. You're going to kick yourself a soccer ball from ground level, and you want it to strike a wall that is 5 meters away from where the ball is on the ground, and you want it to strike a location that's exactly 2 meters high up on the wall. Little contest, I don't know what you're doing. You put some money on it, or you just told your friends that you could do it, but you got to kick this ball and give it a certain velocity, right? So let's say that you're going to kick it at an angle of 30 degrees. So when it leaves the ground, it's at a 30-degree angle. What initial speed do you have to give this ball? So there is the question. So let's model this out a little bit. We've got some distance away. We've got some wall here. And well, let's not make that so big of a distance. So this is 5. This is 5. 1, 2, 3.5. 1, 2, it's like right here. There's 2 meters above the ground level. Here is your ball right here, which is 5 meters away this way. I don't know, does that look like a soccer ball? I don't think so. I don't think so, but that's it. Do we have a big foot here? Big foot comes along. Oh my gosh, this is a really big foot. And what's it attached to? That's attached to some person. Maybe I should just stop trying to draw this, right? Okay, so this foot comes along, kicks the soccer ball, and the soccer ball is going to do what? Well, it's going to leave the ground at an angle of a 30 degrees. So let's say that it is going about like this. We have some V initial hat equals some magnitude V initial at theta V initial is equal to 30 degrees. So what do we want this ball to do? Well, it's not just going to travel in a straight line because now it's a projectile. So what's it going to do? Well, it's going to go up. Oops. It's going to go up and eventually strike that spot is what we want it to do. Now, is that exactly its path there? And the answer to that is no. That's really ugly. I'll do something like that. Is that exactly its path? No, we don't know what its path is. It could still be going up when it hits that spot. It could be going back down when it hits that spot. We don't know yet. But at least we can draw something out so we have some notion of what we're trying to do here. Like that. All right, so the question is, what is the magnitude of the initial velocity that's necessary for that to take place. So how are we going to do this? Well, what do we know? We know this. We know that this is the delta x, change in position in the x direction that this object has to undergo. And this is the delta y, change in position in the y direction that the object has to undergo. So what do we have? Well, we went through a nice little, I don't want to say derivation, but a nice little manipulation in terms of figuring out the displacement delta y as a function of the displacement delta x. And let me see if I remember how that all played out here. We had in the end that delta y was equal to negative g times a delta x squared divided by 2v initial squared times the cosine squared of theta v initial. That seems to be good. Plus delta x times the tangent of theta v initial. So we explicitly got this expression, again, by substitution and manipulation between motion in the y direction, motion in the x direction, eliminated at time in favor of our delta x and our velocity in the x direction, which we could then combine and stuff. So this is what we ended up getting out of this. And what do we do from there? Well, we go ahead and say, well, we want to solve this for this quantity right here. So we can go ahead and start manipulating this around a little bit. We can go ahead and move this over to this side, and then multiply by this, and then divide by that. I'll do this in a couple steps. I know I've done it before. Just go ahead and do it again. And we can say that delta y multiplied by delta x. Nope, not multiplied by. I'm messing this up. Delta y minus delta x times the tangent of theta v initial multiplied by this, multiplied by, this is this quantity, multiplied by 2vi squared cosine squared of theta v initial. That must be equal to negative g times quantity of delta x squared. So what can we do with that? Well, now we can divide both sides by 2 cosine squared theta, and then divide by this as well, this total quantity here. And we can write ourselves that v initial squared is equal to a negative g times delta x quantity squared divided by 2 times the cosine squared of theta v initial multiplied by delta y, multiplied by the quantity, delta y, minus delta x times the tangent of theta v initial. And then what do? We take the square root of both sides, square root. I'll just do it like that, get rid of that. And there we go. That is the magnitude of the initial velocity that is necessary, written in terms of all of these quantities, the angle and the displacements that we require. So what do we have? Again, we've got that delta x is equal to 5 meters, delta y is equal to 2 meters, and theta v initial is equal to 30 degrees. We can go ahead and start putting all this stuff in there, and we'll do just that. V initial is then equal to the square root of negative g multiplied by, let's just say 5 meters quantity squared up. Let's just do 5 meters quantity squared divided by 2 times the cosine squared of 30 degrees multiplied by the quantity of 2 meters minus 5 meters times the tangent of 30 degrees. And there we go. This should turn out negative, cancel out that negative sign, bring it up with a positive, and let's just go ahead and calculate this, see what we get. Being careful putting this in the calculator, of course. I'll use some parentheses all over the place. We've got negative 9.8 times 25. That is divided by the quantity of 2 times quantity of cosine 30. You've got to be a little bit careful with that because you don't want to square the 30. You want to square cosine of 30. So that 2 times that multiplied by this 2 minus 5 times the tangent of 30. And that looks to be good there. I get 13.572. 13.572. Meters per second. So could we check this and just make sure that we've actually got the right answer? And the answer to that is, yeah, sure we can. Sure we can. How? We'd have to go ahead and figure out some other stuff with this and make sure that it all makes sense. But ultimately, yeah, we'd have to see what's going on with this. So let us do this. Let's see. So let's apply the initial velocity. Yeah, okay. So let's just move on to the next part of the problem, and things will kind of fall out of this. So part B. Part B asks, how long is this object, the soccer ball, in the air for? Time in the air. How long does it take for it to strike the wall? Well, there's a couple really easy ways of getting this. And one of them is just to go back to the x direction, right? We have that v sub x is equal to vx initial. This motion in the x direction remains constant for a projectile. And vx initial is going to be equal to v initial times the cosine of a theta v initial. So we've got ourselves that v sub x is going to be equal to 13.572 meters per second times the cosine of 30 degrees, which gives us 11.753 meters per second. And then if we want the time, what do we know? We know that delta x is equal to vxi times t. We can call that sub I, that's fine. We solve this out for time, and we get that time is equal to delta x divided by vx initial, which is then equal to 5 meters divided by 11.753 meters per second, which is approximately 0.425. 0.425 seconds. There we go, there's the time interval that it takes to strike the wall. And then, lastly, we've got ourselves this. What is the speed, or the velocity, excuse me, at which time it hits the wall? So we want to know C, V final hat is equal to what? And it also asks, is the ball traveling up or traveling down? Because it could be going down, or it could still be going up when it hits the wall. So that's going to fall out of what this final velocity is. How do we get the final velocity? Well, again, the final velocity, in terms of its magnitude, is equal to the square, the sum of the squares of its final velocity, which, again, the x velocity is constant. So we've got ourselves vx squared plus vy final squared. Vx final is equal to vx initial. So what do we need? We need to know what vy final is. And how we're going to get that? We're going to get it by knowing the time and the initial velocity of the object and the equation of motion for a projectile. So we've got ourselves that vy final is equal to negative g t plus v y initial, right? Vy initial is equal to v initial times the sine of theta v initial, which will then be equal to Vy initial is equal to 13.572 meters per second times the sine of 30 degrees. So we just half of that. Let me just do this really quick. 13.572 divided by 2. And we've got 6.786. Vy initial is equal to 6.786 meters per second. We know how long it's in the air for. We just figured that out. 0.425 seconds. T is equal to 0.425 seconds. And thus we can go ahead and get what Vy final is. Vy final is equal to negative g times 0.425 seconds plus 6.786 meters per second, which gives us that Vy final is indeed equal to negative 9.8 times 0.425 plus 2.621 meters per second. And Vx initial was equal to our 11.753 meters per second. So, 5, 2, should all work out right. So this is where we can kind of check things out with the initial velocities. Does the ball travel 5 meters in this amount of time if this is its initial velocity in the x direction? And the answer is yeah, we've already solved that. And then the other question is, well, does the ball go 2 meters upward in 0.425 seconds if this is its initial velocity in the y direction? And the answer to that should be yes. That's what we can always go back and check. So we got delta y negative 1/2 gt squared plus Vy I times t. So negative 0.5 times 9.8 times 0.425 squared plus 0.425 times 6.786. 6.786. 0.425 squared. I gotta move that. Plus 0.425 times 6.786. And squared plus that. That is, yes it is right. Didn't put my negative sign out in front. .998, yes. So again, what I just did there was I just made sure that this time, with this initial velocity, gives me a displacement in the y direction of 2 meters, because that's how much it has to displace if this is truly the time, and the y component of this is that, which the y component is this, so it's really testing out this. And we've already shown here that 5 meters traveling at 11.753 meters per second will take us 0.425 seconds. Making sure everything kind of fit, because I will say that it is easy to input something incorrectly in this expression and get the wrong answer. And how do you check that? This is how you check. Go back to the x and y components, and that you need a certain displacement in the x and the y. But here is the final velocity in the y direction. Back to this part. Got a little sidetrack there, but that happens. So now we want to calculate what is the magnitude of the direction. So the magnitude of that final velocity, v final hat, is going to be equal to then 11.753 meters per second, quantity squared, plus 2.621 meters per second, quantity squared, which should give us square root 11.753. 753 squared plus 2.621 quantity squared. 12.042. 12.042 meters per second. All right. And then the other question was, is the object going up or going down? Is it still rising when it strikes that position on the wall, or is it descending? And what do we look at for that? Well, we will calculate the angle, but let's just ask this before we even calculate that. Could we tell? And the answer is yes. Look at the y component. Vy final is equal to a positive here. That means going up. Still going up. Still ascending by the time it reaches the wall. This is not supposed to be a t, but a positive sign. There we go. So let's just go ahead and get what the angle is. We've got theta v final is equal to the arctangent of Vy final divided by Vx final, which is then arctangent of 2.621 divided by 11.753. 11.753, yes. Which gives us theta v final is equal to, it better be positive, but it looks like it's going to be pretty shallow because this is small compared to that. And we've got the arctangent of 2.621 by 11.753. 12.572 degrees. So there it is. Still going up, level enough, getting close to where it's going to start descending, but not quite there yet. There's a fancy little problem. They're cool little problems to kind of deal with. There's a couple in the homework that make you do things similar to this, consider displacements in the x and the y direction, and extract notions out of that. So I'll leave it at that for now, and bid you a farewell, but not forever, just for a little bit. See you guys later.